Hello everybody and welcome to Handmade Hero Show, where we code a complete game live on stream. Before I get started today, I just wanted to mention that after today's normal programming stream, we will be doing a special Sunday stream where we're gonna head over to Jonathan Blow's channel on Twitch, and we'll probably do like a squad stream so you can easily switch back and forth between feeds or something. I don't exactly know how we'll get that working optimally, but we're gonna go talk to Jonathan Blow about whatever we end up talking about. Really, it won't be a constrained conversation, but we're gonna start talking about some parser stuff, and really, it's just an excuse to get together and talk about some programming things because, well, streaming gets a little bit boring after a while, and it helps if you can talk to other programmers about stuff. So I'm looking forward to it. Hopefully, the video feed stuff will work well enough and won't be too much of an issue, but we'll be making the best of the COVID-19 situation and trying to do a little Sunday programming stream where we can hang out and learn some cool stuff from John about, basically like compiler implementation stuff at first. And then if we end up on other topics, we end up on other topics. But that's the idea. So I'm looking forward to it. So stick around for that. And you can, either watch this channel or John's channel is twitch.tv/naysayer88, NAYSAYER88, I believe. So if you want to catch that stream, you can come to either channel and we'll figure it out. So it's this stream right here. So that's what's going on today, and that's all. That's the only public service announcement I had there. So let's go ahead and get started programming. On yesterday's stream, I basically wanted to kind of clean up the way the full cast code was working, and that went pretty well. It's at a point now where we have our input, like sampling information, is now well aligned to what we're actually trying to do. And so we're correctly sampling our octahedral maps, I think, now with a good stochastic sampling that guarantees that we sample one octahedral pixel, one ray out of each octahedral pixel every frame, and that we jitter those pixels in a way that uniformly covers the sphere over time pretty well and on any given frame. So I'm pretty excited about that, and I think that worked pretty well. And if you look at the way the lighting's working now, I think it's going pretty good. So really what I want to do is try to accelerate the raycasting now. Just take a look at where we're slow, maybe why we're slow, what are our options for maybe speeding things up. And then we have to move on to a lighting quality pass. So basically, get the performance of the raycaster going well, because that's going to pretty much be unrelated to the quality. Well, the more rays you can cast, the better quality, obviously, so it's not completely unrelated to the quality. But what I mean to say is our decisions about how to compute the lighting equations are not going to be particularly relevant to how we traced rays quickly. We know that we need to trace our rays quickly and accurately in order to produce good lighting results, but we don't really have, those two systems are not tied together. So we should be able to optimize our ray tracer without any fear of causing problems for improving the lighting equation computations, which is sort of a separate issue. And our lighting's already looking pretty good. The main thing I'm worried about is doing a little bit of smoothing so you don't see voxel edges as much, which is thing one. And then the other thing is, some tone mapping, but also figuring out why we're getting some of the lighting feedback. For example, down here, you can kind of see that simple lights tend to really flood out the rooms down here. And again, some of this is, I think, has to do with also how we're constructing the room. So there's a lot of lighting quality things I want to look at as we go. And, like I said, I don't think that will be a huge problem for us to get going, but it's a separate problem, so I want to leave it for now. All right, so if we take a look, I guess I probably shouldn't have closed that. If we take a look at the lighting debug information, so here's sort of a heads-up display, if you will, of what's going on. Our rays per probe is now locked at 64, which is exactly what I wanted. So we're casting out a 64 point sphere, if you will, and that sphere rotates through over time so that we get more coverage. And that corresponds exactly to the octahedral map. So every pixel of the octahedral map gets one cast out of it. And the reason I wanted to do it that way is just because I felt like that's the cleanest way to write it out. It may not be the best coverage way to do things, and we could consider changing how that's done in the future, but I kind of wanted to start with that streamlined process so we could get any code gunk there out of the way. You can then take a look at what we're doing here. You can see that in general we visit about 5 leaves per cast. What that means, assuming that we're still collecting those statistics properly, which we'll have to do a little bit of verification to make sure we don't have any errant stuff we missed, but what these statistics tell us is that we're generally testing about 5 cubes for every cast. Now that's a pretty reasonable number there. I'm not too worried about that number. And you can also see like how many partitions we visited per leaves cast. But this number is a little more troubling. This 24 partitions per cast, I believe that means we go down 24 checks before we actually get to do an actual test, right? So we're spending a lot of time navigating our bounding hierarchy, and you know that might not be so good, right? And there's probably things we'll want to do to make that work better, right? It's hard to say, but, you know, we have some issues here. So we kind of need to look at how we can get these numbers to look a little bit better, because generally speaking, I would assume, and we can try to make, you know, a little bit, we can try to prove this a little bit more to ourselves as we investigate the code, but trying to initiate about 100,000 casts into the system, 100,000 casts per frame spread over like at least 6 processors is not that many casts, right? So if you take a look at what we're asking the computer to do here, and we come in and we say, all right, we've got, you know, somewhere around 100,000 casts. We're splitting that out across 6 processors. So we're asking for, you know, 20 grand, 15 grand in terms of the number of casts. And if we assume that the processor is going to be, you know, somewhere north of 2 gigahertz always, sometimes as high as 3 gigahertz, you know, if we did want that to be at, you know, at a reasonable 60 frames a second, let's say, and we're just looking at what that's going to imply. So, you know, we're talking about about 33 million, right? You know, somewhere in the 30 million cycles range for how many each of those has. So if we're talking about, you know, if we're basically talking about something where 2,000 ops per ray is what we would need at 60 frames a second, it's not the end of the world. As you can see, it's not as fluffy as you would want, right? Again, these numbers, they multiply out in ways that are kind of non-intuitive. When you think about how fast a modern processor is, it sounds really fast, but once you talk about having to do something at 60 frames a second, suddenly it whittles down quite a bit, right? And when you're talking about something like ray tracing, where you have a lot of rays that you're trying to cast, right? And so you've got just a tremendous amount of work involved there. You kind of have to be very judicious about it. So when you think about the fact that, you know, if I did that back of the envelope math right, and we should probably do a more serious investigation of it where I actually double check and make sure I've got it right a little bit later on. But if we take a look in here as to how our full cast is actually working, so you can see what the routine looks like. You can sort of see that, you know, everything that we care about, for the most part, that's probably going to be slow, happens inside this Raycast call, right? So this thing here, this routine here that does 4 wide Raycasts at a time, that's going to be the thing that really ends up being, you know, this is where all the time's going to be spent. And so if we look at what's going on in this function, you can kind of start to see why we're getting this problem. if you look at what happens inside the raycasting, you can kind of see that although we have a relatively straightforward piece of code, I mean, the number of ops here is actually pretty small. The problem is we've got a fairly weighty set of things going on around it. So this stack traversal here and these, sort of the child op situation going on here, we're just, we're getting a lot of box data, right? Like we're basically pulling a lot of box data out here, and we are suffering for the fact that, when we're doing this, we've got to push a lot of things onto the stack, pop things off the stack, and so on, right? So the fundamental way that this thing works, and by the way, this is probably bad. Sticking an if in here is not a good thing. In fact, it's a very bad thing. So we probably want to do something different than this, right? Like, this is probably not code you really want to have. You don't want any kind of ifs that aren't essential inside your main loop. So I'm gonna go ahead and just nerf these real quick. I don't think that would affect our runtime much, but I just want to make sure that we're getting those out of there. So anyway, all of that is what's happening in here, and we're getting, a total time here that's represented by this line. So pretty much all the work we're doing that we care about's in here, and this work here for compute light propagation, we already optimized a bit, so it's already kind of down in the lower end of things, but it could start to become significant as fullcast becomes optimized. So we really have two optimization targets, and they're the two top things here. Everything else underneath is not really relevant to us. And I also don't know to what extent we're doing a vsync here. I think we're not. Let me see what happens if I turn that on. I don't see really any difference. So I don't know if we're actually getting... I don't know to what extent we're vsyncing and what extent we're not. Like, I don't know if we're getting held up much by the processor here or not. The fact that frame display stays the same... let me take a look here. It's a little bit hard to say. So I don't really know exactly what's going on there. I don't know what we're seeing here. So that's something we maybe have to look at a little bit later. But either way, it doesn't matter. The point is, in this case, we're gonna try and be working on this top line number, and I don't really know that there's much we can do about this value here. So this 6144 for the full cast. I mean, there are some things we could do, right? If we wanted to, we could do some kind of an interleave where we only did every other one of our light voxels. I mean, thinking it through, that top line number, which is how many times we call full cast, we could use some kind of a stipple pattern where we basically say, look, we're going to do like even and odds in like a checkerboard pattern or something. And we just won't actually update anything that's outside the checkerboard pattern. And then we flip the checkerboard pattern on every frame, right? So we could do something like that, and that would also improve the lighting speed by enough to get us to 60 frames a second, potentially. I just don't know what it would look like exactly, but... yeah, I mean, I'm kind of curious. Let's take a look at what that would entail. So, I don't think we have really anything like that in the code at the moment, but if you imagine what that would look like. So let me get the test sphere and move that down. I don't want that in the way there. I'm going to put that over here. All right. So if we take a look at what's happening in fullcast, you can see here that for each one of these fullcasts, it calls it on a particular texture tile. So it's like, I need you to update this tile right now. So that full cast function could just be done like with a stipple pattern, right? So basically we could just say inside here, the Z and Y that we're doing, we'll just take and we'll compute whether or not we do this particular one based on a checkerboard pattern that alternates either frame, right? So, for example, if we did, you know, an X and 1, right? A Y and 1 and a Z and 1, right? That basically tells us like which ones of these, if you think about like the checkerboard pattern, if the X and 1 says, is it odd, right? And Y and 1 says, is it odd? So basically, if we said that we wanted the, well, and I guess I'll do Y and Z because those are in here. So if we basically checked to see what the status was of Y and 1 and Z and 1 and said, look, we want them to be not equal, right? We want to have, if the X is odd, we don't want the Z to be odd, and vice versa. Presumably that would produce a checkerboard pattern that was, you know, uniform through the space. And I'll leave the X out of it for now because that's something we want to compute at the head end since we're doing a single X sheet here. But I could do something like this where we basically said, all right, we're going to have a should compute in here, and then we'll just do it if should compute. And we would go ahead and put the checkerboard pattern in like so. And we probably don't care much about the entropy sourcing at the moment, although in the future we're going to probably want to fix that to be different. But anyway, if we stick a checkerboard pattern in there, right, then what we should see when we run the game is we should see like a checkerboard pattern emerge in the code where we're only actually seeing lighting on the checkerboard. Although, oddly enough, I am not seeing that. What's going on there? Y and 1 not equal to Z and 1. Shouldn't I only get checkerboards out of that? Let me go ahead and draw, just make sure I'm producing a checkerboard here. Let me go ahead into our OpenGL renderer, and I'm just going to go to the end frame code, and I'm going to force it to draw the actual, like, you know, light maps in here. Okay. So I want to go ahead and see, I guess one thing is they will get copied. So I need to start by not copying, I guess, just to see if we actually produce the checkerboard pattern. And I should probably also zoom out and turn off the smoothing. So let's take a look at what that would be in the... So in our vSpan, USpan, I'm not sure exactly what I want to look at here. I guess I'll just widen it a little bit. So I guess I'll just say, all right, the vSpan here will just be, I don't know, 0.25, right? And we'll just take a look at what the vSpan is. So there's the vSpan. And if you look at what's happening here, you can see we're sort of getting a, you know, an obvious dropout of each of the Z rows. But it doesn't necessarily look like it's alternating the Y rows. Did I do this wrong? If the Y and 1, so if, I mean, it seems like that's correct, right? Just checking the lower bit, which will go on, off, on, off, on, off, on, off, right? Across the voxel. I only want to compute it if they're equal. Yeah, I don't really see what would be weird about that. You know what I'm saying? That seems like that should be correct. I guess the only thing, though, is X's aren't parodied. So actually, that may be fine because of the section we're looking at. Yeah, okay. So that might act... That's probably actually right. I'm just probably not looking at it because XY is the checkerboard you're going to see. Z is this way, so I suppose that's okay. Let's go ahead and introduce X then so that each sheet flips polarity. So basically we need something here that's like, you know, like an XOD, right? Where we go ahead and check that. So what we'd want to do here is say, like, I guess if XOD is not equal to those, so we can flip it each time. You know, this should be just something we can XOR, shouldn't it? If they're both the same, it would flip. I feel like that would give me what I want. This is complaining, or was. Oh. Let me just see. That seems checkerboard-like to me. There we go. So now I'm getting the checkerboard. I just forgot that, well, X isn't involved, so that's why you got a singular row there. So if this is the checkerboard pattern, you can see now that, like, the checkerboard, it updates the checkerboard, doesn't update anything else, which is what I wanted. And so what we can do here is just, like, on either frame, we can just do the checkerboard on the frame index as well. So finally, we would do, like, an XOD here with, you know, some kind of a thing that comes in from the actual work itself or from the solution, right? Which is a frame odd value, right? And inside Handmade Lighting, I just say, okay, there's, like, you know, a frame odd value here. And the frame odd value just goes 0 or 1, 0 or 1, 0 or 1, right? So every time we go into, every time we finish pushing a lighting frame, we just say, like, frame odd equals frame odd, solution frame odd, and we just XOR that with 1, right? I guess I'll write this is OX1 for, well, nah, not bother. So basically what we're doing here is just saying, look, just flip that bit, flip that bottom bit, whatever it was. I guess I shouldn't even have to do this, right? That'll just flip the bottom bit by itself. All right. So I'm just curious about this. So you can see at that point, we actually saved quite a bit of time, right? Now it's down at about 20 milliseconds per frame consistently, between 19 and 20, which is almost enough to get us a clean 60, right? And, you know, I don't know, not immediately obvious that you would care that much about that. So that seems like another good option for us, because that way, you know, we're just computing less. Obviously, the easiest way to optimize is just to not run code. You know what I mean? Because that's gonna, there's really nothing you can do there's no optimization you can do that's faster than not running something, right? So yeah. So let me go ahead and turn off that debug draw there. And then we can start to look at, you know, is there a way to speed up the actual raycasting at all? Because any improvement we could make to the raycasting code would be huge for us in terms of being able to improve the speed of the lighting. So as it is, you know, it seems pretty reasonable, right? Like it seems like it's working pretty well. But you know, like I said, I'd like to get it up to 60 or more if I can. Not that OBS can capture that. It drops frames all over the place, but... All right. Oh, and by the way, chat, no, it doesn't make propagation any slower. At all. Right? Because actually, like, I mean, I shouldn't say that. It does make propagation slower in one sense, but not in another, because you see the updates for a given light transmission for however far away it is on the same frame. So you can also, if you want to, blend in faster. And in theory, you might be okay there too. So it does make how do I say it? Propagation is the same speed, but blending is slower. Might be the way to say it. In other words, it doesn't reduce the amount of time it takes from light to get from one side of the screen to the other, which is still instant. What it does do is make the blending half as fast, right? So the amount of time it takes you to get up to a certain blend level is lessened. I don't know if that makes sense. All right, anyway, moving on, let's see what we can do with our full cast. So I'm going to go ahead and take a look at this code and, just see what I can do inside the Raycast function. So when we look at what's happening here, you can see sort of the way that we're going about things is we're doing sort of a traversal of our boxes here. And we're pushing on the first one, right? So we make a little box stack, and we go ahead and push a box on the box stack. We go ahead and look to see out of its children, which ones we want to look at. We loop through those and we continue. Now, one of the things that I'm immediately kind of concerned about here is So I don't really know, to be completely honest with you, that this is a smart way to set this up. And I guess I do feel like, generally speaking, people trace Ray bundles at a time. But to be honest, I guess I'm wondering why they trace Ray bundles at a time. So this is kind of a little confusing, and I suppose I should think this through a little bit more. When I'm looking at this, I'm thinking to myself, I do believe that most of the time when people do ray tracers like this, they trace bundles of rays at a time, which I think is usually the way it's done. But I guess I don't know why they don't just trace one ray at a time and instead test against a bundle of boxes. And I guess I just have no idea why. I mean, that's the kind of thing I should probably go read up on and take a look at what the latest research is on that. But I guess I just don't know why we don't just always do a tree that's got 4 wide. It's always 4 wide. So we always build a hierarchy of 4 wide boxes and then store a 4 wide box that we intersect with. Do you know what I'm saying? So I'm not sure why we didn't just do that. And I even remember us thinking that we would do that. So I don't think we did it out of hand, but again, I don't really know. So I do feel like rather than have... It seems like maybe that's just a mistake. I feel like why don't you want to test against 4 boxes at the same time? Because that way, when you load, you always load 4 wide. So the boxes would already be set up for you to do a 4 wide load on the boxes. So you'd combine your X's, your Y's, your Z's for 4 boxes at a time. And then what you'd do is you would cast against 1 ray. That way, you would always traverse the exact right hierarchy for that ray. And that just seems like it would be way better. I'm going to go out on a limb here and say that maybe the reason people don't normally do that is because they are trying to go much wider than 4. Meaning, you probably wouldn't want a spatial hierarchy that was fanned out on 16s, and like that's more what a GPU has to do. So it could be that like 4 is a good number, like 2 and 4 are reasonable numbers, 16 and 32 and 64 aren't. So it may be that the reason that you normally don't do it that way is because you're normally targeting something that's much wider than 4. That's all I really have. But that really tempts me to want to try rewriting this the other way around. Because I would like to see what the speed comparison is. So what I might say is like, I might say, what if, could we basically like imagine what would this routine look like if it was operating the other way around? So like instead of the Raycast taking the Ray origin and the Ray D this way, it would take, box-wise Raycast or something, and whereas the other one's the Ray-wise Raycast, right? So it would take a single Ray origin and a single Ray D, and it would cast that against the box hierarchy more, by going along the same as the box, by loading the boxes instead. And if you look at what that would do, I'm going to go ahead and leave the debug code in here for now as well. If you look at what that would do, if we imagine that, if we load up things, instead when we look at lighting box, we would have a thing that was like a lighting box for X basically, right? So, every time we push something on the stack, it's 4 boxes. And when we check against it, we would check against 4 boxes, right? So there wouldn't be a loop here. The loop would not exist. You would check against like a 4x box and you'd just do it, right? And again, the reason I like that is because it gets rid of that loop, which I don't particularly care for. So you'd pop a box for X out, and then you would just go ahead and start working with that box. So rather than doing a loft here, which is what we're doing, we would instead just grab these out as actual 4x wide, like these are already 4x, right? So we would, yeah. Does the box P get used here anywhere? We use the center, probably what, to do the radius? Yeah. So I'll leave that like this for now, but I think this is a little suspect. These should probably just be loaded directly. and computed out of hand. So I think we probably want to fix that because I don't think this is set up quite properly. Also, if we look at box radius, right, it's really, yeah, like this code is not doing what we would want. So I think what you probably want to do is you just want to store like these values and use them after the fact, probably. I don't know. We'll take a look at that later, but I just want to look at the effects of doing effectively the same calculation, but I think there's work to be done there. All right, so assuming that we get this stuff, what I'm saying here is that we have array origin and array D, and this is like going to be lofted. So these are the things that'll actually become lofted up from single ones to packed. So now those are 4 wide clones effectively of themselves, right? And so I think that makes more sense anyway. And the tough part at that point is just going in, will be at the end when you want to extract stuff out of here, you only want to extract the one that is the best, right? So but to a certain extent, that is kind of what you want, right? Because we know, because of the limitations of the SSE instruction set, we know that we can't do voxel irradiance wide, right? Because the lookups, like fetching memory, which is most of what's happening in there, is something that can only happen in straight line code. We can't do it wide because the SSE instruction set doesn't have scatter gather in it. If we were AVX 512, we could. No, there are no parts really of that unless you've got an Ice Lake laptop or something. Well, that's not true. AVX 512 is in some of the i9s too. But anyway, so this might, I think this might be worth exploring. So maybe today and next weekend, we can just play around with this and see what's going on there. So if we imagine we're actually doing this code the same exact way, I don't think any of this changes, right? So all of this is exactly the same. The only difference is we take a look to see when we try to figure out whether or not we hit something, we just need to know whether or not we just need to know which sub box to like descend down, right? So we need to be able to push boxes on the stack depending on which one we hit. Like we need to push a different box 4 onto the stack depending on which one we hit. And we would have to push like up to 4 boxes. You know what I'm saying? So in order to do that, I guess that part is a little bit tricky because when you need to actually descend, that part's a little bit iffy, right? I don't know that we need a box child count here per se. But what we do need is child count's fine, I suppose. We just need some way of saying whether or not we push something on the stack or record the hit, right? So yeah, I'm not sure exactly how to do that cleanly. That's a little bit tricky. What we essentially need to do is just a mask extract, and then we need to push on the parts of the mask, like for whichever one. We need to like push on the correct values onto our stack, right? And it's just a little bit iffy because I'm trying to figure out how you would do that without too many ifs. That's the thing that really I feel like is difficult there. Because if you need to push on, like you need something that looks like this. Because you tested 4 box. Oh. Although we could do something even more ridiculous than that. So there's another thing we could do. And that is really weird and probably not a good idea. We could do a thing that basically was there's only one descent. No, that doesn't make sense. But anyway, point being, if we have 4 boxes here, we need to do something that looks like this, where we push 4 boxes on, and we need to push them on based on whether or not we hit them. The reason that that's troubling is because I'm not sure exactly how you would do that in a way that doesn't become ugly pretty quickly, right? You can imagine doing like conditional moves for all of this, I suppose. So it's just like C move, C move, C move, C move, C move, C move, C move. And I suppose that's not that bad because it doesn't change what code is actually being executed. I don't know that I would really have all that much luck getting the compiler to generate that. But, you know, what I don't want is something that looks like this. Because that's just a horrible pipeline flushing nightmare at that point. Because, you know, there's no way it's going to predict that stuff correctly at all. So yeah, that's pretty nasty. That's pretty ugly. Anyway, so if we take a look at what's happening in here, and we look at what this branch does, yeah, this would have to be a kind of conditional move thing where, you know, I don't know what would make the compiler do the right thing here, but imagine something like this maybe. So it would do something like, look, if the mask and foo then do the assignment, right? That kind of thing. And same with the depth. So you could do a thing like this where you just kind of walk through it and say like, okay, you know, see if you can get the compiler to do C moves for each of these things. And then you have like a mask that's like, okay, for the box that we're looking at, we've got our sub box, and we just do something like this, right? And so you have like, if the mask and like, you know, whatever the thing is that you're testing against, when you extract the mask, you would do something like this. By the way, that's probably not what the mask will actually extract to, but, you know, separate issue. It's probably more like, well, I'll be honest. I'm not sure exactly what it would be, but when we extract the mask, it'd probably be byte-wise. So it'd probably be like, you know, bit 1, bit 4, bit 8, bit 12 kind of a thing. You know what I'm saying? But we'll look at that in a second. So anyway, the point is, yeah, you know, it would be something like this, probably. So that way it's just like a big serial dependency chain that can get thrown off to the processor and then the processor can just loop and start computing crap, right? And the downside there is that because of the way we wrote this being depth first, it means that it has to wait on this thing, which, yeah, is not great, right? Because that dependency chains, ugh, so terrible. None of this feels good, I'll be honest with you. So now I'm trying to think, okay, is there some other thing that I'm missing here that's just like, look, there's a better way to traverse this thing? Because what I just want something where it can stay relatively streaming, right? Where it relatively, most of the time, it's just loading boxes and testing against boxes. Because the closer we can have it to just, I load box, I test box, repeat, the faster it's going to run. And the more you have to sit around fussing with stuff like, what am I testing and where, it's just going to go really slowly. So here's another way to think about it, I guess. Maybe another way to think about it is, what if we instead turn this into more of just like a codec style problem? So what if we just said, how about we write the thing that we can actually do, and then we try to make a thing that encodes a hierarchy in a way that we can actually do it, and we just live with those limitations? Like, it sounds stupid when I'm saying it, but it's like, I mean, that's something, right? And so just trying to think it through, imagine, I guess, if we just said, all right, you are doing... You're doing boxes, you're producing a mask. The mask then tells you what to load into the thing to do next. And I guess maybe you can do that. Yeah, I don't know. So maybe this is this is part of the reason perhaps why doing it the other way is better. Although the other way we did it does sort of still have the problem. Like, if you look at what's actually happening in the other Raycaster, you still sort of have the problem. Where's my other Raycaster? There it is. You sort of still do have the problem of the depth push happens and then you immediately have to use it, right? I guess one thing that's worth noting is you don't actually need to push things onto the stack in the case where you are like, if you actually put everything onto the stack instead, you could change the way this loop worked a little bit. So for example, you could, if you wanted to, change it so the source index actually happens in here, right? Now that doesn't seem like a very good idea because that just seems like probably a waste of time. So I wouldn't really recommend it, but yeah. And we have, we can change the hierarchy however we want. So I'm not trying to work with this hierarchy particularly. I'm just trying to think of how we would actually keep the hierarchy, how we would write any hierarchy that allows us to stream boxes cleanly so that we could test against multiple boxes at once, just because that seems a little bit better. And maybe that's not true, but it feels like it would be. So we do know that those 4 boxes can put things fairly continuously for themselves. Oh, actually, I just got an idea. So actually, maybe not. Maybe what you actually want to do, I say. So what if instead we had a lightbox stack entry, and in that we stored which box we were going to look at, but also the mask that we got for that box. And maybe I want that aligned. So if you think about it, then what you would do is say, all right, we got this box stack garbage here. And what we're going to do is we're going to say we get one of these boxes and we put it in here. And then we also put in a mask. And the mask is just whatever the heck the mask is, right? And then what we do is we always load 4 wide out of the boxes. But we only, when we do our tests, we mask the test against the mask we put on. So rather than ever having to do this crap, it's still just this. Right? So when we need to go down another level of the hierarchy, we can just say, like, okay, let's process this box and do this mask. Right? Yeah. Yeah. So that seems good. Because then when you load out the mask, you could just say we're loading up the things out of this box, and we can just mask the results of that thing against what we're looking at here. Now, that's not quite correct because, like there's 4 of these, right? So you test against, you're going to load up 4 separate pieces. But those 4 separate pieces can be the things that are sort of contiguous, right? So when you load up here, you would still do root box, right? And you would still do a loop over the 4 pieces. You just, and when you push each of those on, you then do the test 4 times. Or you push 4 things. Not sure which of those you want. But again, the nice part about that is you just say, look, when we push this on, we just push the mask on, and then that way we know at a time which ones we're doing. I suppose that now I'm thinking about it too, like it's like, all right, is that really any better? I mean, what we could have done is just push all four onto we could always push all four onto the stack and then just zero out the pointer and just check the pointer. Right? So, I don't know. Maybe that's not so hot. Still not sure, yeah. So, yeah, I'm just not thinking of anything clever here. Maybe it's a fool's errand, but yeah, I mean, I do kind of feel like I want to be able to do as many of these as possible, right? And just looking at it, like, yeah, in like my dream world, right? It's, you know, it's gonna be something like this, and we would just, I want it to look as close as possible, just doing all of these things just in a tight loop with nothing else, right? So, like, the best possible case is it looks something like this, right? And you can just loop over this and process as fast as possible. You know what I mean? So that's like what you would want to do. And so the question is, how do you get this part as efficient as possible? The part where you just push on 4 boxes that you're doing. And so, yeah. So looking at this right here, I mean, essentially, there's a few ways we can go with this, right? We could try some pretty ridiculous stuff, where we mask out ones that aren't in the set, right? We let these selects run, so we could do like a child mask, right? That we load out of the box for. And I mean, I guess another way to look at it too would be, since we know whether things are children or not, do we really even need to write the loop that way? All right, I'm gonna delete this for now. I gotta think about this. I think I want to like just let it rot in the back of my brain for a little bit. But just having looked at that, that now begs the question here. So I feel like maybe we want this box to tell us what its children are, right? So if you imagine doing an if here, basically, where we would not have to do the if on the inside of this thing. I feel like that might make a little bit more sense as well. So, like, when we pull off the root box, we would then loop over the children of the root box in a tighter loop if we know that they're actual things we can hit. If that makes sense. So, you know, if you imagine pulling the if, the child count if, out to some other thing. So let's suppose I did like, okay, root box, you know, is leaf container or something. So we just say, sometimes we know this, you know, sometimes we know this thing's a leaf, sometimes we know it's not, right? And then we just specialize these two things. So in one case, we say, all right, like, give me the, you know, give me the version of this that operates one way, and then give me the version of this that operates the other way. So in the case where we know that this thing is a leaf container, then we know that we're always testing leaves when we're inside it. And as we plow through those, we would say that we never look at this case here, right? We just want to know if we're in the any closer case. And if we are, then we're going to do this thing. Otherwise, we won't, right? And we could make this be more streamlined with less ifs. I don't know that we actually want to do that because there's a fair number of computations actually happening in here. But it does mean that like this code goes away, right? So, you know, we only need any closer, right? And yeah, and we could even just say, look, if we stop doing this stuff and we just look at what happens with the if any true here, we could also say, look, maybe that's enough to just run the thing. Right? All right. So, you know, again, just looking at this, like trying to get this down, and we'd say, look, this is what we're going to do for all of the boxes that we're actually testing against. And so that we don't have to, so that we don't have to like worry about it, and we can do it in a more condensed loop. Then the other question is like, all right, when we're on the other kind, so now we're doing partitions instead of leaves, right? In that case, we could also say, look, we know how many there are because there's always two or something like that. I want to say there's like only a certain number of boxes. And that's another, like, fixing that aspect of the hierarchy might be another thing we should probably do at some point, but yeah. So, you know, taking a look at this loop here, we would leave this loop the same, except for now this part goes away, right? And this goes away. So it's mostly just that. Right. And so now we just have two sides of the thing, and we can look at them separately. Again, I'm not sure it makes sense to bother with this because you've got another one down here. So, you know, maybe we do that, and it just simplifies that code slightly. We could maybe turn this into a conditional move or try to, although I don't think it's really going to work. But there would be like a push or should push, right? And then here we would just say, all right, box stack depth equals should push, box stack depth, and we'll assign box back to it. If we want to. Actually, we don't even really need, well, box stack. That way it can see it's a conditional move. And then depth equals should push depth plus 1 or depth, right? So again, we can start to turn these into flatter things. We don't really know that we want to do that yet, but this is strictly for my benefit. Like, I'm just trying to read this and see what I think of it, right? And so at that point, all we would really need to know is, in that lighting box nonsense, we would need to know if something was a leaf. Right? So in here, where we've got, like, you know, is light or whatever, we would just have, I guess it'd just be other flags, right? So in addition to is light, it would be like, you know, is light, you know, is... yeah, I guess it would just be is light and is leaf container, right? And then anyone who actually pushes one of these things on, you know, instead of this sort of thing, they would actually be just when they like push in an occluder or something like that, right? They would just be, you know, setting that to 0. When you're pushing on a light, you would be setting leaf container to, you know, equal like, you know, some flag that equals that. Something like this. And so if we look at where the lighting box is defined, there'd just be, you know, maybe I'll do it like this. Doesn't really matter, but something like that. So, you know, we would set whether or not it's a light based on that, and then here we would just say, all right, is light, is leaf container, if it, you know, ands with. That way it doesn't add any more space. Something like that. This part here, I'm going to go ahead and say we don't really need this anymore anyway. So I'm going to take this out, and we're not really going to use that, I don't think. So. All right. So let's go ahead and get this working now, because I'm curious to know. Oh, by the way, also, since we're not casting here, how fast is this? Still kind of weirdly flickery there of the timing. It's a little bit hard to tell what's going on there. But all right. So anyway, in terms of knowing what to actually test there, what we have to do is we have to actually set that container flag. So when we're doing split box in here, whenever we create one of these boxes that we need to split, don't really know what the if one is here for, to be completely honest with you. I guess we were looking at some kind of non-split case or something like that, but I'll get rid of that now. So if we actually look at how we're splitting up this hierarchy here, which again is another thing we can look at improving, because our hierarchy could be a lot better. But when we, and you know what, this is also a case of something we could do where if we just actually, since it's KD tree like here, we could just start doing it as a KD tree so that we didn't actually have to do a box test now that we'd split the loops out, right? But anyway. So when we come through here and we say we're going to split this box, and we put the children into the box, I guess, you can see like it's setting the child count here. I think all we would have to do is remember whether or not we needed to split any of the children, right? So I think it's just saying, look, loop over the split planes here. If the count A and count B are both, you know, if we actually did a split, then we start to split the children, right? And so in that case, I guess we just need to know so I guess I'm not sure. So when that builds the entire hierarchy just within that one loop, right? You can kind of see it. So I guess what happens is if the source count is greater than 4, it actually tries to do it. If the source count isn't, it just stuffs it in here, right? So I guess all we need to do is find out if we actually did split the boxes and if we change the source count there, right? So we just need to know if we did this. Because if we did this, then there's other split boxes beneath us. But if we didn't, then there aren't, right? So I think that that's all we really need to do. So, you know, I guess we would just do something like this. So then here we just do, look, if we actually split, then we're not a leaf container. If we did, we are? Does that seem right? Apparently not. It's kind of an interesting effect. I'm not sure what's actually happening there. So it looks like that's not quite correct, although I don't actually know. It may actually be correct, and it's just the actual test that's not correct. But yeah. So in here where we add box references and we stuff those in here, right, and we're going ahead and doing is light is leaf container, and we OR that in, I believe, so if we come through here and we've actually split, then the boxes in question are going to be tested against for actual, they aren't going to be tested for actual collision because they themselves might have children. I guess, you know, maybe what we have to do though is verify that the box did get split. So, although no, because it's always going to be a parent box, right? So that's not true. It's creating these boxes here, right? I guess another way to look at it is I guess we don't even really have to do this. We know that anybody who had like well, no. No, I think that's right. So I don't know, that seems right to me. Does it not seem right to you? That feels right to me. I'm not sure why that wouldn't have worked. So I guess we'll have to take a look at the code more carefully to figure out what I screwed up. But it seems like that should be doing the right thing. What are the stats again on that? Total casts initiated, total partitions tested, total leaves used, total leaves tested. Wait, what? Oh, I've got it backwards. Did I get it backwards? No, I didn't. So for each one of these, we're doing total leaves tested. For each one of these, we're doing total partitions tested. So yeah, I mean, shouldn't that work? I don't get it. We should have been seeing something come through here, right? So you're telling me that the is leaf container and, you know, is leaf container there is always set? So actually split is false. If you come through here, actually split is true. So at that point, this is true, you would not OR this in, right? So we should be getting to this case. How are we not? What am I missing there? Because I'm obviously missing something since total partitions tested is never getting hit. So let's go ahead and step in here. I'm going to set this to debug mode because I don't have an idea of why that's failing. And that's in Raycast. So inside Raycast here, I should probably also set us to single thread. I don't know if you can freeze threads. I think like single thread stepping was something that was supposed to be added at some point, but I don't actually know how to do it. And it may or may not be in here. So I'm going to go ahead and turn off multi-threading for a second so I don't have to deal with it. So right here, I'm just going to say, look, go ahead and do the work. That way we only have one thing to look at. So in the Raycast, what I just want to do is see what am I not understanding about what's happening here, because we should hit that case at least sometimes, but we don't. So let me see, like, what does this box look like? What do these root boxes look like? Are they just totally not correct? So this is just 0, even at the root. Wait, but that's correct. So we should hit this. And there's total partitions tested. What the hey? So if total partitions tested is getting incremented, how am I not seeing it? Are we reporting those numbers wrong? There's total partitions tested. Did I miss something? Does that not say what I thought it said? Yeah, total partitions tested 0. So if that's coming back as 0, and yet I just watched it get added, there must be some kind of a thing where it's not actually tracking it properly? Although in this case, I suppose... No, I don't know what... Because here it is, right? We loop over this, we put in a bunch of adds, right? Cast initiated, partitions tested, leaves used, partition leaves used. And I mean, there it is printed out. So, like, what the heck is happening there? So let's do another step in the debugging to find out how we're getting the wrong values. Because that doesn't really make any sense, does it? So I'm curious about this. Here's the call. So I'm going to run through to that call specifically, right? And then what I want to do is I want to look at work to see, like, there's total partitions tested 41,880, right? So then we're going to come through here, and the work count, you know, is whatever the work count is. We're then going to look at each one in turn. There's total partitions tested. So we're going to add that to this. There we go. So are we just like overflowing this variable somehow? No. So that's 1197104 is what we're supposed to be sending out to the debug system. But now it is 0. What? So the first time through, it is correct. The next time through, it's not. Okay. Is it not testing the next time through? So is the lighting hierarchy wrong after a frame? Okay. So we must not be clearing those, I guess. So the two places I know that we can do it is under push occluder and push light. Those are the only two things that we can push, as far as I know. When we actually do our... Oh, so maybe this just doesn't clear anything. I guess it's possible that Splitbox actually is trying to be efficient and just never sets that value. So I guess what we would actually need to do there is set this explicitly. So maybe it really needs to do something more like this, I guess. Okay. I mean, I guess that's efficient. We were trying to be efficient here. We didn't clear, we weren't in a sort of defensive programming clear everything mode because we didn't want to spend that time. So I guess that's fine. All right, now let's see if this thing is actually producing correct numbers. That was cool. I mean, it was bad, but it was cool. So that seems pretty good. Wow. That's running at 50 milliseconds? That's single threaded. How is that running so much faster all of a sudden? Hold on a second. So what happens when I turn on threading now? So that seems pretty cool, actually, right? It actually seems like that makes a substantial difference in the speed, to be completely honest, right? Because that also, that's a bit weird that the frame time doesn't go down by a factor of 6 since these should be independent. I wonder if that means we got some memory boundness happening here. The heck is this? What's happening out here? All right, so we're starting to get somewhere here. Honestly, looking at that frame time, it's starting to look pretty small, actually. The lighting is not really occupying as much time now, and I'm a little concerned as to why it's showing up as high on the profile. I guess this 60 is because it's looking at it across 6 threads. So I think that means the cast is now the same cost as this and the frame display, right? So I think that actually was pretty cool. I guess it's hard to say. But I mean, yeah, like it looks like we're actually in the point where we're gonna have to start fixing the renderer, which is fine. But look at that. Because at this point, I think that clocks is summed. So I think, in other words, let me just to try and put this in perspective. So full cast is threaded. So I think if we actually stopped timing full cast and just timed the lighting update outside the threads, that would be a fairer test. I don't know if that makes sense. But if we effectively said, look, I'm going to time end lighting, which is there, and only that, now you can see a fairer estimate of what's happening, right? So now we're like evenly split CPU, GPU weighting around, right? So I think I was just miscounting that sort of, how fast we actually were. We're actually quite fast. And I wonder what would happen if I enable the checkerboard, or just stop doing the checkerboard now, right? I'm wondering what that effect has on the frame time. Because, yeah, that's just like, we're not even number one on the board anymore half the time. So let's go ahead and take a look and see if we turn off the checkerboarding. So just get rid of that. I'm curious. So without checkerboarding, we do end up a little bit worse, right? You can see now we're consistently on top. So it's still not optimal, right? It's not great. But we're still hitting 30 just fine. Now without checkerboarding on. Right? So that's pretty cool, actually. And I wonder what happens if we turn off the diffuse copy. I'm also curious about that, because that's very expensive. I want to see how expensive that actually is at the moment. So when we actually do our diffuse lighting here, so we could actually also make a substantial difference there, right? By optimizing that code. So by optimizing the copy. So that is now like significantly bad, I would say. All right, so I guess I have a few more questions as well. So if I go now and I say, all right, why don't you try building the hierarchy a little bit differently? So like if I go to Splitbox and I just say, look, how about instead of 4, we say it's 8. How about it's 2? How about it's 4? So it's interesting, like, it's not even sensitive particularly much to us how we're building that hierarchy either. So yeah, I think we're on to something here. I think basically like our Raycast is now pretty much substantially better than it was. Interesting. So I'm also wondering what happens if we cast more rays. Like, how much do these rays actually cost now? I'm actually somewhat confused about that cost a little bit. And I wonder if, you know, if we changed the way we were doing this now, I wonder if we could even do something a little bit different where we said instead, let's cast 4 rays out of the same octagonal slot and do 4 times higher lighting quality that way. Because it looks like actually that traversal is, yeah, like fairly, yeah, Because yeah, I mean, it's really kind of wild at this point. Looking at what we could dig in pretty deep into this, I think, because it looks like we're actually doing pretty well. And looking at the performance here, we're gonna need a more accurate way to measure this. I feel like. Because it seems like almost not that. It's really hard to look at the difference. Let me just. And you see like what's happening here with these slots too. It's just, we're just not having a particularly stable timing here. I mean, it's almost like it doesn't really care what I'm doing. It's surprising how little a difference some of these things make. But anyway, so I'm not sure like that we're doing the best job at how we're distributing the rays at the moment as a result of what we're seeing. So because it may be that if we cast rays that are closer together, we'll get better traversal and end up getting like lighting of similar at a similar cost, but that's actually much better, right? And furthermore, like, yeah, if you take a look at the blending and there's a bunch of other things we can sort of tweak here, right? But if we look at what's happening blend-wise, what I'm trying to do now is figure out what an estimate would be for if we wanted it to be quite stable, what we would have to do. I don't know that I really want it stable. I kind of want it to be flickery because I like that effect. But I suppose I can get that by just flickering the lights. So we may want to do some better sampling integration too, because it may be that like, you know, we can do a better job using the samples we have than we're doing right now. But it looks like if we were to do twice as many samples, it wouldn't look that much different. But if we were to do 4 times as many samples, it would look like this with the same algorithm. And this is considerably smoother, right? And there wouldn't be any lag because we'd be doing 4 times the samples. So I would be interested to know if maybe that's a smart way to go. You see a little bit of on really distant stuff, you see a little bit of flicker still, but otherwise it'd be quite stable, right? And like I said, I think we may be able to change that by perhaps looking at the total contribution that something's making and picking the T update blend based on that. You know what I mean? Just basically doing some importance, like some measure of like importance sampling there to reintegrate those over time. Yeah. So, gosh, yeah, I'm not sure what to do next. It does look like 8/60 is plenty. So if we had 4 times the samples, which we could do, we would basically get mostly flicker free lighting at that point. It looks like. And it would be pretty much indistinguishable in terms of update speed, because you can see, like, I don't really see any lag at this speed. And so if we had the quality of the previous one with the speed of this, that's what we would have if we were doing 4 rays per octal instead of 1, in theory. Like, I'm not sure that's a perfect test, but it's something like that. Interesting. And I guess I also don't know that our entropy is working particularly well here either, but I guess that's sort of a separate point. But yeah, like, so if you imagine, like, if you imagine just doing this 4x, so like, imagine you just did this 4 times, right? So, and it would be faster because we'd be doing it, that means the rays would be in a pretty tight bundle. But if you imagine just doing like, where we're calling the Raycast, so here, right, where we're grabbing out the sampling sphere and we have the entropy index. I mean, I guess I could even just do this in the work load, but if we throw on an oversampling pass here, right? Like so. And we effectively say, all right, the entropy index, you know, is going to be like plus equaled something at the end of this. So if we add a 4x oversampling there, we can sort of see it will be slow, but we'd presumably see what we'd actually get. So that looks like, so that doesn't actually look better, which is interesting. That suggests maybe our sampling is just bad, and that's why we're slow. That's why we're flickery. But so let me just see what's going on here. I guess at that point I should probably also do like, there we go. So yeah, you know, it would look something like this. I don't know how much faster than this it would be, though. You can see here the cost goes up sort of prohibitively for that. But yeah, it could be it. Do we have time to try this? 10 minutes? So the reason that I don't know that I can test it in a short amount of time, but yeah, it does, you know, that's kind of interesting, is all. The reason I don't know if I can test it in a short amount of time is just because if you look at what's happening here, where you look at the spectaxle, the way that the Raycast is working is the Raycast writes out, you know, it does 4 pixels at a time. And it wouldn't want to do that anymore. So changing this is kind of expensive because you really have to make a decision about which one you are doing. And I suppose I could make an if here that, didn't do that. But yeah, if you take a look at what's going on here, I suppose you could do it this way. You'd say, look, here's an if 0. And what we're going to do is, instead of what was happening here, instead of, writing these out, we're actually going to write them out because we didn't cast enough of these, right? Yeah, so we're just going to sum this part here. We're just going to sum up what the answer actually is. And so, like I said, it's a little bit hairy to actually do that. And then when we do this, we would have to do like a load. And then when we would write it out, we would leave the back value the same. So we wouldn't blend in that one. That's what we would do. I'm kind of tempted to try it just to see what happens. It's too much for right now. We'll save that for next time. Let's do the Q&A now so that we can be on time for switching over to John's stream. I'm going to leave it like that. I'll leave it like that for now. All right. Did you notice the instability and timing was connected to the hovering text in the debugger? Oh, okay. No, I didn't notice that. One of the problems that we have, and we probably will have to fix it eventually, is that our debug UI is too expensive and, for profiling work. So we probably need some way of isolating that, This is why oftentimes it's better to use a separate machine for profiling. It's why things like RAD's telemetry program, they're like a separate server that you run, and you just send packets to it. So you do have to pay the cost of sending the packet, but you don't pay the cost of anything else. And that's a good way to do it, because again, when you're trying to look for performance things, it's really too difficult sometimes to make it go integrated into the app like that. It's for Coder, is the editor. So the flickering in the lighting is because it's undersampled. So rather than doing sort of a fake lighting where we just slap a sphere around the character like you would normally see in 2D games, we're actually doing full indirect light transport, like entirely, right? So it's like a full ray tracer in there computing the lighting. And because ray tracing is very expensive and currently we just do it on the CPU, we've considered moving to the GPU, but if we move it to the GPU, then you basically are only going to be able to use it on like an RTX card or something, right? Because we already use the GPU to do compositing and stuff, and We use a lot of cycles if we want high res, anti-alias free, and so on. So because of that, we don't have very many samples to send out. And so the flicker comes from the fact that the light from the samples that you send out through each texel of the light map, you only sometimes hit the light sources and sometimes don't. And so you're trying to do an integration over a whole like region there, right? And doing it stochastically like that adds noise to your system. So what you're seeing is the noise of the sampling. And more specifically, if you wanted to imagine, I could draw you a diagram that maybe helps understand a little more intuitively what's happening there. So like if you look at, let's see here. So if you look at what's is seen, if you will, from a particular texel. So from a particular texel, you have to imagine like, okay, we've got a light map, right? And there's some data in it or whatever, right? In fact, let me go ahead and grab a grid there. So, we're computing a light map, and we're basically saying each one of these texels is a light source, and we're saying that maps to a sphere, right? And we're saying that, like, so for example, this quadrant of the upper hemisphere of the sphere maps to, this part of the light map, right? Or whatever. So what we're effectively asking is, what is the total for one of these texels? Like, let's say this texel right here, and maybe it maps to like right there, right? We're effectively asking for that shaft of light. So for the shaft of light that's going out of a particular texel, right? We're asking what is the total amount of light that's coming in through that shaft? That's effectively a camera rendering problem, right? You're effectively asking, what do you see when you look out through that texel as a window? So if you're shooting rays out there to find out, what you end up with is something that if we now imagine here's the texel and we're looking outward, so we're looking out through this texel, we're shooting rays and we're just seeing what comes back, right? Now, when we get an answer, when we see what the light is that comes back, what we get is something that's a crude approximation of the light in that area. So maybe there's a light source here, right? Let's say. And maybe there's a wall that's a fairly bright reflector here, right? As we're taking these samples, we're starting to get a better picture of what's there. And if it was static, after a while, we'd just have a fairly complete picture of what was there, because we'd have so many samples that we can basically say we've reconstructed what the incoming light is. Because we need just the average, right? All we need is the average. But since these things are moving over time, like the light's like moving this way, whatever, we can't just take a long-running average. We have to fade out old samples over time so that as things move, we stop counting them. So as a result, at any time, we're really only looking at like, maybe 16 samples worth. And we have to reconstruct this exact picture from just those 16 samples. As we get more or less samples that fall inside or outside of a bright light source, that's where you see the flicker. Make sense? So what we can do going forwards, like I said, is be a little bit smarter about how we're integrating those samples. Don't always use constant weighting. Use weighting based on what we see and how much it contributes to the particular texel and so on. So we can probably do some kind of importance-based weighting of our results that would be better than what I'm doing now. The reason I didn't throw that in already is I'm not a sampling theory person, so I don't really know offhand what we would do. So I need to think about that and like maybe I may need to go read a little bit up papers on it to see what we should be doing there, right? As previously mentioned in chat, both isLight and isLeak were OX1. Oh no! How did that not cause a bug for us? I guess you just wouldn't see it. Oops. Oh, well, you know what? I guess the reason that... I guess now that I think about it, that can never happen anyway. We shouldn't have even bothered with this. It should just be is light or is leaf container. Yeah, that was dumb. Talking about character movement, will we implement a transaction system, something like John's? We already did. So that's how our character movement works. It's a transactional movement system. That's why, in fact, I was one of the people, the person advocating to John very often, specifically that. I was like, I love transactional systems. You should do one. We've talked about it a bunch of times, and he was... There's reasons to and not to do them, and he's been on the fence about it. He eventually just committed to the transactional system because I think he just felt like there's no way to really get a puzzle-based game working properly that way, which is also my opinion. For ours is an action game, so maybe that's not true, but I just feel like transactional-based systems don't have the same kind of gameplay bugs that non-transactional systems do, so I prefer them. So we've always been transactional ever since the early days of when we started doing the hopping mechanic, because once we had the hopping mechanic, I'm like, all right, I want this to be transactional because people are either on a square or they're not, and I'm never going to allow two people to be on the same square, so it's got to be transactional. Let me see. Take another question or two here. I think I told John 2:30, but I don't know. He may be ready now. So, in fact, let me just check and see what John's status is, if I can check to see what John's status is. All right, he said 2:30 on Twitter, so I guess I'll just do until 2:15 for the questions, and then at 2:15 I'll switch to trying to get John to hook up on video chat. Just trying to, because I'm sure we'll need at least 15 minutes to make sure that the video chat works properly and is streamable. So and then we'll just plan on starting at 2:30. Is this already the best lit 2 but 3D game in the whole history of gaming? I don't know. No, I don't think so. We might be by the time we finish some of our quality passes, but no. Are you using a diffusion heat model to average the texture samples over space and time? No, we don't diffuse over space at all. The reason we don't diffuse over space is because lighting doesn't diffuse through space. I mean, that's just doesn't, right? Light is transmitted in lines because photons travel in straight lines. That's just how it works. So we don't do that. We do average texture samples over time, but the way that we do that is we bias towards more recent samples because we want the lighting to be responsive. Now, like I was saying before, I think we will want to change a few things about how we're doing that averaging. So I don't think what we're doing right now is particularly good. I don't know that a heat model is anything we particularly want to use, but we probably will have some more importance-based integration happening to try and make for better use of our samples, and also to try and denoise. So one of the things that we probably can do is try to figure out a little bit more specifically what's happening in terms of when we cast, and potentially save more information than we're saving now. Here's a crude example. Suppose we sampled the specular lighting, and I don't think we can do this because I think it's too expensive, but suppose we sampled the specular lighting at 16 times the resolution of the diffuse. So rather than storing one texel, we store a grid of 4x4 texels for every specular slot. But we only store it. Then what happens is every time we cast out a ray, we overwrite one of those slots completely. Then, to produce the diffuse lighting, we average that 4x4 down and use that result. Now, why is that useful? It's useful because that takes our sampling jitter out of the solution, because rather than integrating over space, over multiple frames, I shouldn't say space, over directions every frame, we are only integrating, we're integrating over all directions every frame every time, right? So it doesn't have a lag to it. So that way, if you hit the light source in one direction, you didn't hit it in another direction. Then currently that introduces flicker. But in this system, it wouldn't, because you wouldn't be overwriting the bright sample. You'd just be overwriting a direction that previously had a dark sample anyway. So the average of those every frame would still come out to the same thing. So that's why I say it's possible that we can do something much smarter in terms of how we're storing or integrating our values that would make it so that we would eliminate that flicker without casting more rays. I didn't explain that well, but I do think there's ways we can do it that don't have the directional variance. Because if you remembered more about what directions you'd looked, you wouldn't have that variance. And so that suggests to me that we can do a better job with the information we have. Because we know that if we stored that extra information, we could, without casting more rays. Same rays, just more storage, right? Is it okay to use some features from later versions of C++ I may find useful, for example, lambdas or templates? I guess what I would say is it's always okay to use anything you want to use as long as you've done the due diligence to determine that it's actually saving you development time. That's really the key thing to remember. So I don't find C++'s features save time in the long run. They may make you think you're saving time, but when you add up all the other costs, bad error messages, longer compile times, worse code generation, blah, 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 I typically find that pretty much anything you use from C++ ends up hurting you in the long run. Not because it has to, but just because they always do a bad job, right? All of the things in C++ could have been done as good features, they just weren't. So the reason I don't use them is because I think they're actually a bad trade-off. That doesn't mean that you have to think they're a bad trade-off. You can go assess that yourself. And so the only thing that I urge people to do is actually seriously assess it. C++ programmers, almost universally in my experience, do not actually assess it. They claim that something is better and they don't actually verify that, right? Obviously, the C++ committee doesn't verify it, but I mean people who then use those features in their code base. And when I say verify, I mean you have to verify it across everything, all costs, the total cost of development, not just that you saved a few lines of code somewhere by using this template or whatever, right? But if you've actually done that work, then you should not only feel free to use the feature if you've found that it actually can be verifiably better, but you shouldn't need to ask me about it at that point, obviously, because you've done the work. You've proven that for the way you're programming and in the code base you're working in, it is more effective. And that's what you need to know. It doesn't matter what I think, and it also doesn't matter what I think about my code base, because your code base will differ and your development processes will differ from mine. And so that's what you need to verify. And as long as you've done that verification, I would say feel comfortable using anything you want. Feel comfortable using JavaScript through Emscripten, through a Rust translator that outputs Java bytecode. If you've verified it actually saves you total development time for the same end project, if you've actually done that work, then you have nothing to worry about. The thing that people have to worry about is making these choices without any analysis, right? That's the only thing to worry about, because computers are discrete and analyzable. You can tell whether or not you're producing quality code, and you can tell how fast you're producing it because you've got a calendar, right? So you can measure these things at least to a first approximation. And if you have measured them, you should feel comfortable. If you haven't measured them, you shouldn't feel comfortable just doing what I'm doing either, right? You should learn those skills. And when you're a beginner, it's okay to just say, well, I'm just going to program the way Casey does because I know it can't be that bad since he's obviously able to do it, right? That's fine. But as you get better and you become more of an expert, then that's not okay anymore. It's not okay to just say program the way Casey does because he must know, because he doesn't know, right? He's not working in your system. He doesn't have the same brain as you. He doesn't have the same teammates that you do. He doesn't have the same end goals that you do necessarily. So the trade-offs that Casey makes and the trade-offs that you make are not going to be the same trade-offs necessarily, right? So as you become more of an expert, I expect you to analyze those yourself. And if you happen to come to the same conclusions that I do, totally fine. But you don't want to count on the fact that I made exactly the right decisions for your code. And that goes for everyone. Anyone who sits around telling you that they have the right way for you to program is wrong. They may accidentally be correct about the conclusion, but they are wrong about the claim that they knew it was right, because they can't. Would you mind explaining transactional and versus what? Sure. So transactional movement systems, or transactional gameplay systems in general, something I've worked with for a really long time. And in fact, the Witness collision detector even was this kind of system as well. Although since it doesn't have multiple people, the transactional part doesn't have to do much. But the idea is broader than any real specific implementation. It's just about saying, look, there's two ways that we can express the core gameplay of any given game. One way is a chaotic system that just has a bunch of floating point simulation code, and whatever comes out, the end of that is the game, okay? And this is a Unity game or an Unreal Engine game, like anything made in those systems is this way. It works by saying, I throw a bunch of entities into a system. There's some kind of a physics system tying it together. The things like move around and they bump into each other or whatever. And then just whatever happens when the collision gets resolved, I have like vent that fires and it does something, right? And the game is created organically from those things, and the game designer piles enough rules on top to make the game that they're making, right? Now, the problem with these kind of systems is bugs are everywhere. People are accidentally getting shot through the world, or, you know, people get clones of treasures, or they're able to, like, run up the side of the wall or whatever. And that's because it was just a paintbrush model of painting rules and events on until it sort of looked like it was the game, right? A transactional model is the opposite of that. That's saying we're going to approach this like a traditional game, like chess or something, where the rules are 100% explicitly written. If this is the situation, this is the outcome. And all of the outcomes have been pre-analyzed, right? Now, this has pluses and minuses. The pluses are the design is explicit. You know exactly what it is, and you know all of the possible outcomes from that design, right? Because you can literally look at them like a chess tree. And maybe you can't quite look at the entire analysis because you can't afford enough AWS time to actually search the entire tree or something, right? But at least you know, like on chess, you know the space of all like roughly possible things that can happen more or less, right? However, the cost of it is that chaos isn't there, right? You now have a much more conceived, overtly designed system. And the things that will happen in it are more deliberate. So if you're trying to have some ridiculous thing like that happens in Grand Theft Auto, where it was considered a bonus that somebody accidentally like shoved dynamite into the shark, which it caused the tail to explode off at a very high rate, which, you know, kind of caused this bug where a ship flipped around 180 degrees, which is never supposed to be able to do, but that was great and everyone loved it. Right? That's a feature. You know, sandbox games want lunacy. They're not trying to make a deliberate, controlled experience. They're trying to let things get out of control. Right? And so, you know, that's what's happening there. So, all right, I think I'm going to go ahead and stop the recording now. I'll keep the stream running, but I'm going to stop the recording now, and we're going to try and switch over to John and see if we can get video uplink working. So